Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing okay. Let's jump into it. I think I left you guys with some examples to do last time. Let's see. Okay, maybe we'll talk about, just review a little bit what we did last time, and then we'll jump into more curve sketching. So last time did some examples about finding absolute maximums and minimums, which for continuous functions on closed intervals, they're guaranteed to exist. We use the closed interval method where we find the critical points. We evaluate the function at the critical points. We evaluate the functions at the endpoints, and then we compare all the y values. The largest one is the absolute max. The smallest one is the absolute min. That's kind of the process on that. And in terms of problems, problems of this type, they're not really going to get any more complicated than this. It's always going to be sort of that format. Just going to say, hey, here's a function, here's a closed interval, find the absolute max and min on that interval. Okay, so that is good. Very standard problem. We also spoke about asymptotes, how to find them. We care about two specific ones, the horizontal asymptote and the vertical asymptote. To find the horizontal asymptote, what you do is you take limits. Take the limit as you approach infinity of a function as well as negative infinity of a function. And if either of these guys give you a constant, then y equals that constant, which is the equation of a horizontal line, will be the horizontal asymptote. Whenever rational functions have horizontal asymptotes, then whether you go to positive infinity or negative infinity, you'll get the same answer. So you can only do one of them if you want, as well as just know that polynomials themselves do not have vertical or horizontal asymptotes unless they are literally a vertical and horizontal line themselves. So yeah, we did some examples of that. So you need to remember how to find limits at infinity and all that good stuff. And then we moved on to vertical asymptotes. Now, this is when a graph shoots up or shoots down, approaching a vertical line, potentially never touching it. And that's the technical definition. It's just saying as you approach some particular x value, you will either shoot off to infinity or negative infinity if you approach from either the right or the left. That can be complicated to do in general, but for us, chances are if I ask you about this, it's going to be of a rational function that's not a polynomial. And those guys, it's easier to see where the vertical asymptotes occur because they occur when the denominator is 0 after the function is put in reduced form. So we did some examples of that. So you had a vertical asymptote here for this function, 1 over x minus 2. The second function, x over minus 4 over x minus 2, turns out x equals 2 makes the denominator 0, but you could simplify and get rid of this problem. So you don't get an asymptote in that case. You get a whole. So you have to check the denominator being 0 after it's put in reduced form. Okay, cool. Did a bunch of examples like that, even sketched a graph in the middle of it. We're going to sketch another one of those today. Yeah, then we moved on to curve sketching, where we're actually going to combine a lot of things that we've spoke about before and a lot of things you've spoken about since you were in pre-calculus. So the idea here is I can give you the equation of a curve and you will sketch it in more detail than you're used to probably. So that's what this thing is about. And while admittedly, this is not really something that's going to help you in real life, it is something where I can actually test that you understand the important concepts that we've been talking about. It's a visual representation of how well you understand things. And so that's pretty good. So there were 6 steps to sketching a function. One is to observe the domain because that's very important. You might go through and do some computations and it will appear that certain points have certain properties, but they actually don't because they're not in the domain. So you should know what the domain is. You should find the x and y intercepts if possible. That's going to be nice to know. Find the asymptotes if possible, because that's going to be important to know. Then you're going to do the first derivative test and the concavity test. The point of doing the first derivative test is to find out when your function is increasing or decreasing when it hits local maximums and minimums. And the point of the concavity test is to find where the function is concave up, concave down, or where it hits inflection points. And after that, you can sketch the graph, and I'll know that you know what all these things actually mean. When you say a function is concave up, do you know what that means? I will see it visually, whether or not you know what that means. So that's cool. We also spoke about rookie mistakes, but we'll get there. We actually did one example, which is an example that you guys should know how to do by heart at this point, but I just decided to show you the process of going through it. So as you can see, we did the domain, then we did the intercepts, then we did the asymptotes, then we found out where it was increasing and decreasing. And again, it might look like 0 was a maximum here, but it was not a maximum because when we found the domain, it was not in the domain. So that's why the domain is important. So we can tell on the intervals where it's increasing or decreasing, whether it has maximums or minimums. This function did not have any. Then we moved on to the second derivative to do the concavity test. This is where we can tell where it's concave up or concave down. Then we actually graphed it. And we graphed it by going through this process, plotting the important points, putting in your asymptotes, writing your intervals below the graph. This is intervals of increasing and decreasing, as well as intervals of concavity. And then you graph it, obeying everything that you've set out before. And we got this graph right here. And I asked you some things to try for next time, which let's go. So that's where we are. Quick recap. So I know I asked you guys to do sketch B, but I've kind of already sketched B. So I think I want to do something different, moved on to C. There was the example we had when we were doing the absolute max and min, that was the function B in part B. And I did actually draw that for you. So it's a W. I mean, you could do it anyway. You probably did it and you would have gotten a W, and you would have been able to, I didn't sketch this in detail this time, but you would have been able to identify like inflection points like here and things of that sort. When it's concave up, when it's concave down, when it's increasing, when it's decreasing, you would have been able to identify specific points where that happened. You would have been able to identify what specific point it hits these numbers. So you would have been able to do all that. But since we already actually did it, I don't really want to do it again. So I'm actually going to do part C for you. Made an executive decision. We're going to do this guy. Then we're going to jump down to these harder examples. I want to do this guy. And I'm not sure. I might do one other one, but I probably don't. So the thing with curve sketching, and this is something you should know, maybe I should put that. So a couple things you want to know about this. One, handout is on the class webpage. Okay, so if you lose this or I move too fast for you to write something down, you can always pull up the PDF on your own. The second thing you want to realize is that these problem types take a long time. And I say take a long time as far as our class is concerned. This is like the absolute max, really. This is curve sketching problems will tend to be the longest problems you have in this class in general. Like it will be the problem that takes the most time. So I don't really want to do a lot of examples because it's going to waste a lot of time. I will if it's like super confusing, but I don't think it will be if you remembered all the things that we did before. But you should take 10 to 15 minutes on any of them. So when you're practicing on your own and you want to know if I were on a test or a quiz, how would I be doing? Then you want to get the correct answer. You also want to get the correct answer in less than 15 minutes. So whenever I'm writing an exam or something like that, and I'm thinking about, oh, how much time should I give for this exam? If there's a curve sketching problem on it, I'll like put aside 15 minutes for a curve sketching problem. If you can get it done sooner, that's all the better. You can have more time to work on other problems. Most students, I don't think will be able to do it one in less than 10 minutes, but you might, and that's awesome. So I'm saying 10 to 15 minutes ballpark is where you should be. If we're talking about something like a related rates problem or an optimization problem, which I'll mention later, those guys are around 10 to 12 minutes, maybe. Maybe even less if you get really good at them. But yeah, so curve sketching is just understand it's a fact of life. It's going to be one of the longer type of problems. Just get used to that. That's totally normal. But at the same time, you do want to keep timing in mind here. So maybe the first couple times you do a curve sketching problem, you might take even longer than 15 minutes to do it. That's fine. But you need to work to be able to do it in 15 minutes or less. But yeah, 15 minutes for one problem is a very long time, relatively speaking. So we have some examples here. This one is done. Did that last time. So we're going to move on to the next example. Part C, where I want to graph this guy for you because we already graphed the other guy, part B. So let's actually do that. Okay. So find all the important features listed above and sketch this graph. We know all the important features. Those are the features that go through the first 5 steps of the 6-step process. That's what I mean. So let's actually do that again to make sure that we see what's going on. So, all right. First thing you want to do, domain. Right. So for here, it's a polynomial. So domain is all real numbers. Okay, cool. 2, next thing you want to do is find the intercepts. They're going to be 2 kinds. They're going to be X-intercepts and they're going to be Y-intercepts. Okay. So remember for the X-intercept, you would set Y equals 0. Okay, so that means you have x to the 4th minus 4x cubed equals 0. And now you want to solve for x. Hopefully we know how to do that. You factor out an x cubed, you'd be left with x minus 4. So you get x equals 0 or x equals 4, and those are your intercepts. Okay, cool. Y-intercepts, you'd set x equals 0, in which case you would get y equals 0 to the 4th minus 4 times 0 cubed, which is of course 0. That's the y-intercept. But of course, if the x-intercept is 0, you will have a y-intercept being 0 as well. So those are our intercepts. That's the second thing that we do. Third thing we're going to want to do is find the asymptotes. We're looking at a polynomial that's not a straight line. It has none, right? So HA, none, it's a polynomial. And VA, none, because it's a polynomial. It's nonlinear, especially. So you don't have to identify the nonlinear part. You just tell me it's a polynomial and I'll take your word for it. Okay, so for polynomials, the asymptotes part is easy. So here we're going to do where it's increasing, decreasing, maximums, and minimums. And here we're usually referring to local maximums and minimums. Okay, because usually I won't restrict you to some interval when curve sketching. So how do we find maximums and minimums and increasing and decreasing? You use the first derivative test, which means you're going to need the first derivative. So the first derivative is going to be the derivative of x to the fourth minus 4x cubed. It's very easy with the power rule. So it's going to be 4x cubed minus 12x squared. Okay, so that's the derivative. And now we know we want to find the critical points. So here you're going to set f prime equals 0 or f prime undefined. F prime is a polynomial, it's never undefined. So we only care about f prime equals 0. So this means I want 4x cubed minus 12x squared equals 0. 4x squared is the common term. So that will leave me with x minus 3. And so you get x equals 0, x equals 3. And then you're going to put those on a number line in the first derivative. So you're going to put down a 0, you're going to put down the 3. You're going to plug in random numbers in between these guys. It doesn't matter who you pick. So I just picked some nice numbers that it would be nice to work with. And yeah, so technically, if I pick a number between 0 and 3, I could pick 2.7398276. But why? Pick 1, right? It's easy to work with 1. It's also tends to be nicer to plug in these values in the factored form of the derivative. Why we care about signs, not actual values, right? So you just want to know whether it's positive or negative. Now, when it's in factored form, it's a kind of easy to see that because each factored form is going to be simpler than the original equation. So you can plug in a number into it and you can see what's going on. So for example, if I wanted to plug in 4 into the original form of the derivative, I would have to 4x cubed, I'd have to cube the 4, minus 12x squared, I'd have to square the 4, I'd have to multiply by 4. It's going to get really annoying. However, in this factored form, it's a lot easier because 1, notice that the 4x squared is always going to be positive. So there's always going to be a positive term in front. And x minus 3, when I plug in 4 into that, it's easy to see that it's going to be positive, right? So it's a lot nicer to plug things into the factored form. So that's what we're going to do. So if I plug in minus 1 into the factored form, I know the 4x squared is going to give me a positive. And if I plug in minus 1 into x minus 3, it's going to give me a negative. So I have a positive times a negative. That means that I have a negative. Similarly, if I plug in 1 into 4x squared, that's a positive. Plug in 1 into x minus 3, that's a negative. So here it's still negative. Plug in 4 into 4x squared, of course, that's a positive because it's a square. And plug in 4 into x minus 3, that's a positive. So that's a positive. Now, remember in the first derivative test, this tells you about increasing and decreasing. So the negative tells you that you're moving down, down. Positive tells you that you're moving up as you go from left to right. So now that you see that, and you know that the domain is all real numbers, and you see that we decrease on the left of 3 and increase on the right of 3, that actually tells you 3 is a max, right? Min, sorry. Right, because you're decreasing, you hit 3, and after 3 you start increasing. It means 3 was the lowest value that you hit, because we know that the rate of change at 3 is 0. So at 0, 3, you're kind of like bouncing off a horizontal line, which would your tangent line would be a horizontal line. So now I know that 3 is a minimum. We would want to know what this is. So to find the point, you would use f of x. You would use the original function, right? So you have to know when to use which function. If I want to know the actual coordinate that is the minimum, I don't use the derivative, I use the original function. So here I would just have to find f of 3, right? Now f of 3, what was our f? I think it was x to the 4th. So that's 3 to the 4th minus 4 times 3 cubed. Yeah. Right. Now for that, 3 cubed is a common term. If I factor it out, I'd be left with 3 minus 4. So that's just 3 cubed times minus 1. That's minus 27. So the point is 3 comma minus 27. Right? That's the minimum point of this function. So that leads us to a nice little summary that we can write in here. You want to write down increasing, decreasing, max, min. So for this function, notice that we're increasing on the interval 3 to infinity. Notice that we're decreasing from negative infinity to 0, as well as from 0 to 3. And notice that we don't have a maximum. But notice that we do have a minimum at 3 minus 27. And so that's this subsection here. So normally when I give you a problem like this, I'll specifically ask you to find where it's increasing and decreasing, find where there are maximums and minimums. So this is going to be a part of your answer as you go through the problem.
Quick question.
Yes.
So let's say, like, hypothetically, where that -1 is, if that was increasing, we would have a maximum there, right? And like the second was decreasing. If that was,
you mean like if this was going like that?
Yeah.
Yeah, then 0 would be a maximum.
Yeah. Okay. Got it.
Because you're increasing on the left, decreasing on the right, and 0 is actually in the graph. It's in the domain.
Yeah. Okay.
If 0 were not in the domain, then it wouldn't be anything. Okay, so now, yeah, we have that. I do want you to just, I mean, it should be obvious, but just in case, notice that these guys here are intervals. I'm using the notation that looks like coordinates for intervals, but I want you to appreciate when I tell you about increasing or decreasing, I'm not giving you coordinates, right? So that 0, 3 is not a point. It's like the interval between 0 and 3. And the points are the guys here. The maximums and minimums are the coordinates. They're not intervals. Okay, so we have that. So we move on to the next stage, which is stage 5. This is where we care about concave up, concave down, and inflection points. And we know for that, we will use the second derivative. So the first derivative was 4x cubed minus 12x squared. So the second derivative is going to be 12x squared minus 24x. So again, we want the critical values here. Let's call them critical points. So we need f double prime equals 0 or f double prime undefined. F double prime is a polynomial. It's never going to be undefined. However, where it hits 0 is when 12x squared minus 24x equals 0. I can factor out a common 12x. That will leave me with x minus 2. So I get x equals 0 and x equals 2. I'm going to plot that on a number line in the second derivative. Plug in random numbers. Say like a -1, a 1, and a 3. I'm going to plug it into the factored form. Plug in -1 to 12x, you get a negative. Plug in -1 into x minus 2, you get a negative as well. So this is a positive over here. If I plug in 1 into 12x, that gives me a positive. If I plug in 1 into x minus 2, I get a negative. So that's a negative right here. If I plug in 3 into 12x, that's a positive. Plug in 3 into x minus 2, that's also a positive. So that's a positive here. So remember in second derivative, positive means concavity. So concave up, concave down, concave up. So I'm up like a cup, then down like a frown, then up like a cup, right? So that's talking about the shape of the graph. So now we can remember that an inflection point is just a point where we switch concavity. So 0 is going to be an inflection point because it's in the domain, as well as 2 is going to be an inflection point. So once we do that, we're going to find the y value. So we want to know f of 0, which we know is 0. So the coordinate is 0, 0. All right. Then we want to find f of 2, which is going to be 2 to the 4th minus 4 times 2 squared. Just make sure I remember x to the 4th minus 4x cubed. See, I forgot. All right. In which case, 2 cubed is a common term. I can factor that out. I end up with 2 minus 4 here. So that's 8 times minus 2, minus 16. So this is 2 comma minus 16. And so we can do our little summary here. Concave up, concave down, inflections. So we're concave up from negative infinity to 0 and from 2 to infinity. We're concave down from 0 to 2. And we have inflection points at the origin and at 2, negative 16. So that's this section here. And again, intervals, these guys are intervals, and these guys are points. So that's that subsection. Now, it turns out these are all the information that we need to sketch the graph. So that brings us to step 6, graph. And remember, we have a certain order in which we want to do these things. I have some big negative numbers here, so let's do that. So remember, the first thing we're going to do is we're going to put in the important coordinates, right? So the important coordinates are the intercepts. So x equals 0 and 4, the y-intercept is 0. So 0 and 4 are important points. Other important points where we have maximums or minimums. So 3 comma minus 27. So let's put in 3 and that is, let's pretend that's minus 27. Okay, so we know that this is going to be our minimum point. Okay, what other points are important? The inflection points. The origin is one of them. So I can just label that here, inflection. And 2 comma negative 16 is one of them. Okay. So the first thing we do is put in important points. The second thing we would do is put in asymptotes, but we don't have any, so I'm going to skip that. The third thing we're going to want to put in is our intervals. So the intervals are the intervals of increase, decreasing, maximums, and minimums. So we're increasing from 3 to infinity. We're decreasing from negative infinity to 0 and 0 to 3. So here, I know that from here forwards, I am from here forwards, I am increasing. From 0 to 3, I am decreasing. And from 0 going back, I am decreasing. All right, cool. The other intervals we'd put in is intervals of concavity. I'm concave up from negative infinity to 0 and then 2 to infinity. So from negative infinity to 0, I am concave up. I am also concave up from 2, that's kind of line up here, to infinity. And concave down in between that. Right, so this is kind of lining up with that. This is kind of lining up with that. All right. Now it turns out we actually have everything now right on this picture to actually sketch the graph. Once we've actually put all this stuff there, we never have to look back at that stuff. You should be able to sketch everything by just looking at this picture, right? So that's why we take our sweet time to plot everyone on this thing. So now how you actually sketch this is you know that you need to pass through all these important points. You need to pass through here, 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 here. And then the intervals below tell you how you should be behaving as you're passing through these points. Obviously, you should be decreasing the whole time if you're going to pass through the first 3 points. And then to go from the third point to the fourth point, you'd have to start increasing. So that's pretty intuitive there. However, notice how you should be shaped while you're increasing or decreasing. So from negative infinity to 0, you're decreasing, but you're concave up. So you're decreasing and you look like a smiley face. And this is going to be something that I expect you to graph, right? I should see that in your picture. Between 0 and 2, you're still decreasing, but now you switch the concave down. And I should notice that on your picture. Between 2 and 3, you're still decreasing, but now you switch the concave up. And then from 3 onwards, you start increasing and you're concave up the whole time. So we can tell all of that from the graph. So that's what we're going to do. So in this region here, we're decreasing, concave up. So I'm decreasing, but notice I'm bent this way. If you were to graph, if on like a test or something, someone graphed this, you would lose points for that because you just graph something that's concave down. You should know what concave up means. Okay, so that's what that would look like. Then I know in the next region I'm still decreasing, but now I should shape like a frowny face. I should be concave down. So 0 was an inflection. Now the shape looks like that. So it goes like. Now after that, I'm still decreasing, but concave up. So now I look like that. And then after that, I'm increasing concave up the whole time. So that's our graph. So smiley face, frowny face, smiley face, ends it off. Yeah. That's how we can graph a polynomial in great detail. Now you can tell where the minimum values are, maximum values are, how it's shaped while it's passing through certain points, all that good stuff. Before this, like back in pre-calc, you could only really tell the maximum or minimum if you had like a quadratic, right? But if anything else, you could never tell how high or low it goes. With calculus, we can now tell. So that's what the graph would look like. Okay. Another example. So this is a type of example that might show up on like a test or a final even. Right. And the problem statement is also going to be very similar, right? So I'll do something like this. Consider the function f of x. The formulas for the derivative and the second derivative are given, and you don't need to verify them. Find all intercepts, asymptotes, relative extrema, intervals of increasing, decreasing, intervals of concavity, inflection points, assuming they exist, of the function. Use that information to sketch the graph. So you see, here's the question where I specifically ask you for everything. And so you have to show everything, and you can box them as you're moving along so that I know that you've shown everything. And then you're going to use that information to sketch the graph. Okay. And then I'll give you that. So with these, notice that I gave you the first derivative and the second derivative, even though technically you should be able to find it on your own. I don't want you to have to worry about going through the quotient rule and then making a mistake, and then everyone gets a different derivative, and then they're graphing different things. It'll be a nightmare. So on top of that, chances are if this shows up on a test or in the final, I would have already tested your ability to take derivatives. So I would already know whether or not you can do the quotient rule, right? So I'm not going to test you again on the quotient rule in this problem. So whenever I want you to graph something sufficiently complicated, I'll give you the first and second derivatives. It's what I'm looking for is, do you know how to use that information? Like if I gave you the derivative, do you know what to use it for, when to use it, how to use it? That's the more important thing. So that's what we're going to do here. And we're going to go through the process. Now, yeah, you'll notice things like it didn't ask you to find domain, but I would still find it because, like I said, if you find points, you want to know whether or not those points are actually valid to be something. So I'd find it anyway. I'd usually go through all 6 steps that I gave you guys, even if they're not specifically required. I would go through them anyway and just box the answers for the things that were specifically required. Okay, let's do this. So this is our function that we're going to graph, x squared over x squared minus 4. So 1, domain. At this point, you should realize that the domain cannot include 2 or -2. So that's our guy, right? X squared minus 4 equals 0. You get x equals plus or minus 2. So you cannot be plus or minus 2. You have to avoid plus and minus 2. So, all right, cool. Moving on to one of the intercepts. So we're going to find X-Intercept. So this means you need x squared equals 0, or let me write out the whole thing, but so that of course means that x squared equals 0, and that means that x equals 0 is your X-intercept. Remember, a fraction is only 0 if the numerator is 0, and you need to make sure that what makes the numerator 0 does not also make the denominator 0, because that would be an issue. The Y-intercept right, here's where you set x equals 0. So this means you have 0 squared over 0 squared minus 4 is going to be your y, which is just 0. So you know that y equals 0 is your y-intercept. Okay, so moving on to 3, going to look for asymptotes. This guy's not a polynomial, so we have to be a little bit more careful. We're going to have to do some work here. Horizontal asymptotes. This is where you find the limit as you go to the left and the right. Infinity. So limit as x approaches infinity of our function, and we find the limit as x approaches negative infinity of our function. What is the limit as x approaches infinity of that guy?
One.
Yes. So it's the ratio of leading coefficients. And of course, it's going to be the same if I went to negative infinity. Right? So as I mentioned, these guys are going to be equal whenever you have a rational function that isn't top heavy, these two are always going to give you the same values. All right, so that's that. What that means is the fact that we took these limits and we got a constant number, we got 1, that tells you that y equals 1 is a horizontal asymptote. Now we move on to the vertical asymptote. Now for the vertical asymptote, remember you put f in reduced form. And this is already reduced. Right, you can't really factor or cancel anything. And then you just set the denominator equals 0. Those guys are your vertical asymptotes. Okay, so for the horizontal asymptotes, limit as x approaches infinity and negative infinity of the function. If you get a constant number, well, if it's a number, it's a constant. If you get a constant, y equals that constant is your horizontal asymptote. For the vertical asymptotes, reduce your function, make sure you cancel anything that needs to be canceled. Also notice that if you cancel something, it gives you a whole. And other than that, now you afterwards, after reducing, you find what makes the denominator 0, even after you reduce, and that thing is going to be a vertical asymptote. Okay, so 4, we're going to do increasing, decreasing, maximum, minimum. For that, we need the first derivative. The first derivative was given to us, and the problem says we need not verify it. First derivative is minus 8x over x squared minus 4 squared. So you're supposed to know that what you're going to do here is find the critical points. This is where f prime of x equals 0, or f prime of x is undefined. We have both. This one when x equals 0, because that's what makes the numerator 0. This one, it's when x equals plus or minus 2, because that's what makes the denominator 0. And so now I'm going to test that in the first derivative. I have 3 points to test: 0, minus 2, and plus 2. I am going to plug in random numbers in between these: minus 3, minus 1, 1, 3. And I'm going to plug them into the derivative. Notice that the derivative, the denominator is always going to be positive whenever it's not 0, because it's a square. So the denominator is always going to be positive for all of these. So you only have to look at the numerator. So if I plug in -3 into -8x, I get a negative times a negative, which is a positive. So that's a positive over here. And so that's overall a positive. If I plug in a -1 into -8x, then overall that is a positive. So it's a positive here. I plug in positive 1 into negative 8x, I get a negative. If I plug in positive 3 into negative 8x, I get a negative. So we're increasing, increasing, decreasing, decreasing. Now, question, is 0 a maximum? Yes or no?
Yes.
Yes.
Yes. Yeah, because 0 is in the domain, right? Right, 0 falls in here. And at the same time, we're increasing on the left, decreasing on the right. So 0 is a maximum. Notice that there are no minimums. And we also know that f of 0 equals 0. So that's the origin, 0, comma 0. So now we can actually do our little summary, increasing, decreasing, max, min. So we're increasing from negative infinity to negative 2, and from negative 2 to 0. We're decreasing from 0 to 2, then 2 to infinity. We have a max at the origin, and for mins, we have none. So that's step 4. Moving on to step 5. Here's where we have concave up, concave down, inflection points. For this, we'll need the second derivative. And that, again, is given to us. This is 3x squared plus 4 over x squared minus 4 cubed. So you should know that what you want is critical points. This is where f double prime equals 0 or f double prime undefined. Notice this has no solution. For a fraction to be 0, the numerator has to be 0. But the numerator is 3x squared plus 4 times a positive number. It's never going to be 0. The smallest that x squared can be is 0, and then you're adding 4 to that. So the 3x plus 4 is going to be 4 or bigger. Then you multiply that by 8. It's always going to be positive. It's never going to hit 0. So there's no solution there. However, for undefined, the denominator can be 0. So plus or minus 2 is where it's undefined. And this is something that we already know as well. Once a function itself is not defined, the derivative is not going to be defined. We spoke about when the derivative does not exist, and it does not exist when the function is not continuous. So at minimum, wherever the points that are not in your domain will be critical points every time. And you might have more than that. So here, there are only 2 things to test in the second derivative, minus 2 and 2. Plug in random numbers, minus 3, 0, 3. Notice that in this function, the numerator is always going to be positive. So now we only have to watch the denominator. If I plug in a minus 3 into x squared minus 4, I would get 9 minus 4, which is positive. And when I cube it, it's positive. So that's positive. The same is going to happen if I plug in positive 3, by the way, because it's a squared. So I know that that's going to be positive as well. Then for 0, if I plug in 0 into that, 0 squared minus 4 is negative. Then I cube it. You cube a negative, you still keep a negative. So this is negative overall. This is positive overall. This is positive overall. And here in the second derivative, that means something else. It means concave up. This means concave down. This means concave up. All right. So from that, do we have any inflection points here?
No.
But at -2, we switch concavity. Inflection is when you switch concavity, right?
Yeah.
But they're not in our domain.
but they're not in the domain. So no, they're not anything. Correct. So -2 and +2 are not inflections, even though we switch concavity, because they're not in the domain. So these guys not in domain. So not inflection. Not in domain. So not inflection. Okay, so there are no inflection points. So here we can do our summary: concave up, concave down, inflection. So concave up from -infinity to -2, and from 2 to infinity. Concave down from -2 to 2. Inflections, there are none. This leads us to step 6, where we're going to actually graph this guy. And let's begin. So what do we do when we're graphing this guy? First thing, put in all the important coordinates. The X and Y intercept are 0, 0. So we'll put in that coordinate. All right, cool. What other coordinates? We have a max. So that'll be important. That's the origin. We don't have any inflection points. So this here, we can also label it max. That's all our important points. Now we're going to put in the asymptotes. There's a horizontal asymptote at y = 1. So I'm going to go right here. Y = 1. Kind of should have done the thing with my mouse. Vertical asymptotes. We have 2, I believe.
2 and -2.
Yeah, 2 and -2. So now I would have at 2, -2. Well, vice versa. This is -2, and that is 2. So this is x = 2, so vertical asymptote, and here x = -2, so vertical asymptote. After we put in asymptotes, next thing we want to do is put in our intervals. We're increasing up to -2, and then from -2 to 0. So from here back, we're increasing. And from -2 to 0, we're increasing. Then we're decreasing from here to 2, and then all the way forward. So that's our interval of increase and decrease. Now we want intervals of concavity. I'm concave up from -infinity to -2, and then from 2 to infinity. So here, going back, I'm concave up. And here, going forward, I'm concave up. And I'm concave down in between those guys. There are no inflection points. So that's the whole graph. Yeah. So now we have to know how to graph it. So there are a couple things you can do here. You can plug in points, plug in some test points to kind of see where things are, kind of feel the graph out, and make sure you're doing following the guidelines that you put on the graph. But you can also do things where it kind of makes sense just conceptually, which I suppose will take a little bit more practice. So for example, if I were to ask myself, could the graph be in this region? Well, how would it have to behave if it's in that region? Well, it would have to be decreasing. So I know it would have to do something like this, right? Now, if that is the case, because y = 1 is a horizontal asymptote, there needs to be a point where I have to come back and then level off. Now, if that happens, I will create a minimum point. Therefore, it cannot be in that region, because there is no minimum point there. In fact, there are no minimum points anywhere. Could it be in this region? And again, the answer is no, because I'd have to be decreasing. So something like that. And if I'm doing that, I will create an X-intercept, and there is no X-intercept there. Therefore, it cannot be in that region either. So it means that the graph must be entirely in this region, right? So you can actually just look at it and just kind of see, well, if I look at the regions as they're dissected by the horizontal line, where can it be? And you'll realize that if it had to be in some location, you're going to realize that something will get messed up if it's in a certain region. The graph has to be entirely in that region. Now, because the graph needs to be decreasing for the entire time in that region, and it has to level off at the horizontal asymptote as well as shoot up to infinity at the vertical asymptote, the graph must look like this. Right? It has to look like that. There's no other option, right? That is concave up, and it's decreasing the whole time. It approaches the vertical asymptote and the horizontal asymptote. It doesn't create anything that it shouldn't create, like an X-intercept or a minimum or a maximum. That's the picture. For similar reasons, the left side has to look like that as well. Right, so we know what the left and the right have to look like. Now, in the middle, notice that I'm increasing up here, decreasing right here. I hit a max at the origin. I am also concave down, shaped like a frowny face here. And I'm still concave down, shaped like a frowny face here. So that kind of tells you the middle sort of looks like a parabola, but it's not a parabola because it's stuck between these vertical asymptotes, but it kind of is going to look like a parabola when you graph it. So now you know in the middle, yeah, it has to look like this. And this. So that's the graph, f of x in red. So that's what our graph will look like. Okay, and that's curve sketching in a nutshell. I would practice the rest of these, of course. So, you know, I would do a couple of these, just make sure we have an idea. And I would do both of these. You can also do this one, at least. Chances are, if I ask you to sketch something, it's going to be a polynomial or it's going to be a rational function. And in the event that it's a rational function, I'll give you the derivatives. Okay, so it's that. Now I want to introduce a new idea because I kind of want you guys to be practicing it over the weekend. So it's the next section, optimization. So obviously that's optimization. Let me check where this is. .6. We move on to section 4.6, optimization. Okay, again, handout can be found on class web page. It's a very fancy P. Okay, so you can find the handout on the class web page. So we're going to talk about this. Try to do a very simple first example just to kind of illustrate what's going on. And then I'll leave you to try the rest. Optimization, super important. The main ways that derivatives are used in real life would be like linear approximation, which we covered, and optimization. Optimization is just the act of making something better within certain restrictions that you have. So you want to do something better, make it faster, use up less resources, things of that sort, but you want to do it in a world where you know you have restrictions. So you might have a business and you want to know, how can I maximize profits? And you might say, oh, well, I want an infinite amount of money. But of course, to get an infinite amount of money, you might need an infinite amount of employees, an infinite amount of products, an infinite, right? So it's like, oh, you can't have an infinite amount of money. So now you're like, what is the most amount of money I could have, given that I only have this many employees, this many products can be created, this many blah, blah, blah. So within a world of restrictions, what is the best you can possibly come out with? That's what optimization is. We say we optimize a situation when we make it as good as it possibly can be within certain restrictions. Okay, so that's the basic idea behind optimization. Turns out derivatives can help us with optimization via this process. Again, it's a 6-step process. I don't know, it's coincidence. All these handouts have 6 steps in them. I didn't do that on purpose, but that's just how it worked out. Like related rates, you're going to read the problem carefully, because you have to understand that it is an optimization problem. So usually you're going to describe some sort of situation, and you want to make something as good as it possibly can be. It turns out that often what this means is maximizing or minimizing something. So if you're looking at profits, you want to maximize. If you're looking at cost, you want to minimize. If you're looking at, as we're going to see here, a farmer wants to plant the maximum amount of crops, then he's going to need the maximum amount of area, things of that sort, right? Now, if possible or necessary, just like before, you're going to draw and label a diagram. So geometry is again important here. You want to make sure you understand the situation. Unlike related rates, though, you're going to need 2 equations in this scenario. So there's going to be one equation called the constraint equation that is meant to describe the restriction that you have. And usually it's going to be the thing that tells you the given value. Oh, you only have 50 employees, or you can only create 5 products a day, or something like that. It's going to be a very specific value that's given to you that tells you these are my limits. I cannot pass this, right? And you're going to need an equation that describes that thing. That's called the constraint equation. You also have to find something called an objective equation. So the objective is the actual thing. So what I just spoke about was the constraint equation. You also need an objective equation. This is the equation that describes the actual thing that you want to maximize or minimize. So this would be the equation that would describe the profit or the cost or the area of something that you want to make as big or small as possible, right? So you're going to have to come up with two equations for this guy. The fourth thing is you want to maximize the objective function, find a maximum or minimum of it, but chances are it's going to have several variables in it, and we're not in calculus 3. We can only differentiate things with respect to one variable. So what you're going to do is you're going to take the restriction, the constraint equation, you're going to solve for one of your variables in terms of the other, and you're going to plug it into the objective. The point of doing this is to get your objective function in one variable. That way you can start to do derivatives and find maximums and minimums. The fifth thing is you're going to find the absolute maximum or minimum of the objective function. This is going to help you find what is going to maximize or minimize your process. And that will actually help you to find what the optimal solution is. And I say absolute max and min because, like I said, there's always going to be a restriction. So you can think of this as it being some interval that you have to stay within. So the maximum or minimum might show up on the endpoints. That being said, in a class like this, that is rarely the case. You might see that in homework in a few odd examples, but chances are you're looking for the relative max and min. But technically, you should be finding the absolute max and min. But usually, it's going to be equivalent to the relative max or min. So you're going to do the first derivative, find critical points, all that good stuff. Then finally, you're going to answer the problem. So usually, there is going to be a question that is phrased. How many products should we create in order to have the maximum profit? Which means at the end of the day, you need to say, oh, you need to make this many products. You need to answer the original question that was asked. Students often forget that, but don't forget, there is going to be a problem that you need to answer. It's going to be a word problem, and you're going to want to solve the problem for someone who comes to you for help, essentially is the idea. And I have a lot of examples here. I think I want to do the first 5 examples. And I would say you guys should do the other 2 just for some extra practice. They might be more difficult than the others. So problem 1 is actually a great way to illustrate the process. Sometimes when I'm teaching in person, I actually do problem 1 while I'm explaining the steps. So we're going to do that. We're going to do problem 1 now. Okay. So this is the topic of optimization. So here it is. A farmer has 100 feet of fencing. He wishes to make a rectangular enclosure. He wants the enclosure to encompass the maximum possible area so that he can plant the maximum number of crops. What should the dimensions be? So this is an optimization problem. Why? You have a restriction, 100 feet of fencing. That's your restriction. Or constraint, as you would call it. He wants to make a rectangular enclosure. What does he want to do? He wants it to have the maximum possible area. That is the objective. Right? You need to maximize area. Now the question also asked, what should the dimensions be? So this is the question you must answer. Okay. Now this is an optimization problem. Notice that it's not like a related rates problem. They didn't tell me the rates of change of anything and then ask me to find a rate of change, right? They described a situation about a farmer. They told me I want to maximize something, and then they asked me a question as to what needs to be done in order to maximize that thing. Now, when doing that, you are going to go through this process, always this process, always in this order. So 1, you're going to read. Reading is fundamental. 2, you're going to draw a diagram of possible or necessary. So he wants a rectangular enclosure. The obvious diagram is a rectangle. We need to know the dimensions, which is length and width, which means we don't know the length and width. So I'm going to label the length and the width. Notice that there are tons of options, right? There there are many options, right? He could do, with 100 feet of fencing, 40 and 40 and 10 and 10, or he could do something like 25, 25, 25, 25. He could do something like 30 and 30, 20 and 20. We want the best option. Right? That's what optimization is. You need to find the best possible option, the best possible scenario. But this is our diagram. We need to identify the length and width. So now we move on to 3, where we look at our equations. Equations plural. There's going to be a constraint equation and an objective equation. The constraint describes your restriction. What is our restriction? We have 100 feet of fencing. What is representing the fencing in my diagram? Well, the lines around the box. In other words, it's a perimeter. We know that perimeter equals 100. It cannot be whatever you want. You have 100 feet of fencing. You don't have an infinite amount of fencing, right? You can't fence the entire world. You can only fence a rectangle where it's 100 feet around. So having my diagram, now I know what the perimeter is. So this means I need that 2x plus 2y must be 100. Notice that this also means that x plus y must be 50. So I'll take that as my constraint equation. Now, the objective is to maximize area. So my objective equation is obviously going to be an area equation, because that's what I want to maximize. So that's going to be area equals length times width, right? Move on to the 4th step, where we're going to find the new objective. You're going to solve for one variable in the constraint, plug it into the objective. So if x plus y equals 50, this means that y equals, let's do x. This means that, let's do y. Y equals 50 minus x. This means our area equals x times 50 minus x. Right? Or in other words, our area is 50x minus x squared. Right? This is your new objective. Notice that before our objective had 2 variables in it, x and y. Now it only has 1. Now, once we have a function now that describes the area, that means we can do calculus with it. So 5 is where you want to maximize or minimize, depending on the problem. Now we read the problem, that was step 1. No, we know we want to maximize here. Either way, what we're going to do is we're going to find the derivative and then find the critical points. So you're going to have 50 minus 2x equals 0. You're going to get x equals 25. Now, usually when you have one answer, that's going to be the answer. But you can test to make sure, or if there are several. So here, notice that you can have, and by the way, x is the length. It's a length, right? So the smallest it could be is 0. The largest it could be is 100. Now notice that 0 and 100 does not solve your problem, because if there is 0 length, you don't have an enclosure. Also, if you put all 100 feet of fencing on the length, it means you have 0 width. You don't have an enclosure. So the solution is not at the endpoints, right? So that should be obvious. Not solution, not solution. However, we do have a number to test, which is 25. And you're going to realize that if you plug in, you would get something like that. If you plug into like x times 50 minus x. But x equals 25. So now, it's the last problem. Now you're going to answer the question. So we want the dimensions. That is length and width. So we know that the length is x, which is 25. Now the width is going to be y, which we know is 50 minus x. So that's also 25. So this means dimensions are length equals 25 feet, width equals 25 feet. So it's actually a square. The rectangle with the maximum area is a square. Another way you could say this is that dimensions, it's a 25 by 25 foot enclosure. But at the end of the day, you have to solve the farmer's problem. You have to tell him what dimensions does he need. You need 25 feet along the length, 25 feet along the width. This will give you the maximum possible area. That's it. That is optimization. So 1, you read. 2, diagram. Your diagram is going to represent a whole infinite host of possibilities. You need to find the best one. In order to do that, you're going to find the constraint and objective equations. Constraint equation describes your restriction. Objective equation describes what you want to maximize or minimize. But it has 2 variables in it. We don't know how to deal with 2 variables. We're not in calculus 3, we're only in calc 1. So we're going to solve for 1 variable in the constraint, plug it into the objective, get the objective in 1 variable. Now we have the objective as a function. We can maximize or minimize it by finding derivatives, testing endpoints, and testing for local maxes and mins. Whenever you have 1 answer, that's going to be the answer, really. But you can test it if there are several answers. And you should test the endpoints technically, but it's very rare that the endpoints are going to give you the answers. The endpoints are going to be like, oh, that's not even possible to create something now. And so after doing that, after finding what you need to maximize or minimize, you answer the question. So here the question asks for dimensions. It might not have asked for dimensions. The question could have asked me, what is the maximum area? In which case I would take 25 times 25, and that would be the answer, which is 625, right? So it's possible that they asked me, what is the maximum area? And the answer in step 6, I would tell them, oh, 625 square feet is the answer. But they didn't ask me that. They asked me the dimensions. So I have to tell them, oh, length is 25, width is 25. You have to answer the question. So that's it. Try these for next time. And we'll stop there. Yeah, that's it. Okay, that's it. Here are some more optimization problems that you should try for next time. And again, they'll be in the notes and you can find the handout on the class webpage. So that's it. Thank you for your time and attention. I will let you guys go. Have a good weekend and I will see you guys in the next one.
Professor,
Huh?
I have
Yes?
a quick question. The homework, I think there's more like Cengage that needs to be there. I don't know. It's only like chapter 3 on there. I think it was.
I think it's up to like 4.2 at some point. But I have to put in more homework. I'll do that.
Okay. Thank you.
Yeah. All right. Okay. All right. See you guys in the next one.